In this video, I'm going to be talking about the Riemann zeta function. And the reason I'm going to be talking about it is because I love the history of this function, and I love the things that I've learned while using it, and while struggling with it, and while using it to investigate the Riemann hypothesis. And I feel like I'm at the point where I'm holding lots of individual puzzle pieces and I'm trying to glue them together. And when I try to put this in manuscript form, they're just not quite fitting right. And my hopes is by verbalizing my ideas and presenting them, maybe it'll help me better see the path forward, or perhaps someone watching this video might see a connection that I've missed. So that being said, let's get into it. With that being said, let's talk about what the zeta function actually is. So this is one in front of you. This is one particular representation of it. There's this leading term, and then we have an infinite sum. And this infinite sum can also be known as the Dirichlet eta function. And I'll talk about why I like this representation a little bit later. So I'll remind you that S indicates that our function takes a complex argument. So an argument of the form a plus bi. And this representation is valid, or it converges for any a greater than 0. Why that is relevant is that the Riemann hypothesis involves the study of where this function equals 0. So for what input s do we get back 0? And all known zeros occur when a equals 1/2. So because our representation is valid for any a greater than 0, we can further investigate the zeros of the function with this representation. Now this Dirichlet alternating sum has good intuition for me about what it's saying. Not necessarily in this form, because this is very condensed notation, but if we actually expand that out to see what it's saying, you can readily see the pattern. So it's this alternating sum of 1 over 1 to the s minus 1 over 2 to the s plus 1 over 3 to the s. And this parallels the original formulation of the zeta function, which is just an infinite sum. So it's pretty much exactly the same, except for it's a plus and a minus. But this sum, this addition and minus, this back and forth alternating sum is what I picture in my mind's eye when I'm working with the zeta function. Although when you're working with complex numbers, it's oftentimes better to think of it as a rotation as opposed to just purely a plus or a minus. So with that being said, I'll see you in part 1. Hello and welcome back to this video on the Riemann hypothesis. So this is part 1. You could also call this puzzle piece 1 because I'm going to be introducing the first part of my 3-part series on the Riemann hypothesis. And the first thing I'm going to do, and I hope you forgive me for doing this, is that I'm going to introduce a new function. And I promise that this new function will be the last function I introduce in the video. So just bear with me. So here's our function. F of x equals 1 over 1 minus 2 to the ix. And I just want to draw your attention to the parallels between this and the leading term of the zeta function we defined in the introduction. You can see they're quite similar. This function was derived from the zeta function, but I'll spare you the details of that process, and I will instead show you what this function looks like when graphed, because that's the relevant information. Here we have the graph. I will bring your attention to the fact that we give this function an x, and the output of it is some complex number, i.e. a plus bi. And in particular, the real part returned from this function is 1/2. And you can see there's asymptotes for the imaginary parts, spanning from infinity to negative infinity. So the natural question that I investigated is that if the values returned from this function fit the format of 1/2 plus bi, can we take the output of this function to produce the zeros in the zeta function? i.e., zeta of f of x equals 0. And what values of x produce that result? And the answer is yes. In the first solution set, or the first x values that produce zeros in the zeta function, look something like this. Now, when we put this x into f of x, what do we get out? We get negative 2n. So the negative even integers, which otherwise known as the trivial zeros of the zeta function, aka zeta of the negative even integer equals 0. So that's neat that our function can produce the trivial zeros, but there's another solution set, the one corresponding to the non-trivial zeros. And those values of x look something like this. Now, the general form is the same, but where we have this integer input, we now have a relationship related to the zeros of the zeta. So what do we get when we put this x into f of x? We get 1/2 plus bi, which is what we are hoping to achieve. Meaning that we can vary x to find the specific values of x that produce a 0 in the zeta function. AKA similar to above, where zeta of the value equals 0. And you probably might have noticed a problem. The obvious issue here is that in order to produce the nth zero of the zeta function, that's what this b sub n is denoting. So b of 1 would be 14.13. b sub 2 would be 21.022. In order to produce the nth zero of the zeta function, we have to know the nth zero of the zeta function. So it doesn't really get us anywhere, but what it does is it draws a parallel between this solution set and this solution set. So what I'm asking you to consider is that this distribution is somehow related to this distribution. And if we take a plot of these, we get something that looks like this. And if you're like me, I like to expand these to better visualize. Think of this as if n is 1, then this would be 3 over 2. If n is 2, it would be 5 over 4. If n is 3, it would be 7 over 6. So instead of thinking about it like this, you can instead think of it as the log of all odd integers over all even integers. And the distribution of these values looks something like this. So obviously they're not scaled the same, but their general form is similar, which is not that surprising because it's both the graphs of a logarithm. And I'm not asking you to buy this. In fact, I'm not even trying to sell you this connection. But what I am trying to do is infect your brain with the idea that this distribution has something to do with this distribution, which comes from the trivial zeros, has some correspondence with the distribution of the non-trivial zeros, and which is a topic we're going to explore in the next part. So thanks for watching. Welcome to part 2, or the second puzzle piece. So in this portion of the video, we're actually going to be using the zeta function, and we're going to kind of get more into the meat of my argument. So I have in front of you the zeta function as we defined it in the introduction. And I again just want to remind you that this is how I think of this function. And for our purposes, I'm just going to slide this over because I'm not particularly concerned about the leading term, which will become apparent as we use this. So this is what I want you to picture. Now, when we actually, and this is going to be a little crude, which is the point, when we actually evaluate z of s, so we code it up in Python or Wolfram Alpha, and we look at this as it goes term by term, we can plot out a trajectory. And in all cases, we started at 0, we make some movement, and then we make another movement, and then we rotate. And what we end up looking like is a trajectory that oftentimes spirals or curves randomly, or seemingly randomly. But what happens when we have z of s, where s is a 0 of the zeta function, this sum will converge, and it converges to 0 rapidly. So all together, meaning that at the end, it kind of makes a straight line back to the origin. Now, that's interesting, but rather than me draw crudely what the trajectory looks like, I can just show you what a trajectory does look like. So this is the real part of 0, 1. And the first thing you'll notice is that it's kind of zigzag up and down. And again, that's the result of alternating sign. So up, down, up, down, up, down. But I'll draw your attention to right about term 5, where it seems like we start getting a turn up, but instead we stay low. So it looks like we have a missing peak. Now that by itself is not very convincing. That's just an observation. But this phenomenon or occurrence is easily observed in all the other zeros. For example, in 0, 2, the same thing happens around 5, 6, and 7. So we have up and down, but a flattening, and then back to up and down. And even further if we go out, so if we go to the 61st zero of the zeta function, I find this one particularly interesting because you can see the appearance and exceedingly long duration of that flattening of the curve. Now, that's not mathematically rigorous, right? That's just an observation. But what we can do is try to formulate or investigate exactly what is occurring at these points in time. For ease of presentation, I'll select 0, 1. And again, the terms that I'm interested in are those that I'm interested in what happened at term 4 and 5, because it seems like it should be jumping up, but instead it stays flat. So I'm trying to characterize what exactly to call this. What is this? Why is this happening? And why does it seem to happen in every zero? So I'll leave that up for reference. Now, we are interested in, let me get my notes together, term 4, which is just this one. Although in our case, this b would be 14.13, because that is the first zero of the zeta function. And then we're also interested in term 5. So these are just simply specific complex numbers. So it's 4 to the bi, where b is equal to 14.13. So we can plot these and see what they look like. First off, we have this. For 4 to the bi. And for 5 to the bi, we have this complex number. They're of similar magnitude, but they are in exact opposite directions. So there's 180 degrees between them. Now, if we were summing these together, these would cancel out. But because we have an alternating sum, we can think of these as having an opposite sign. Now, what that looks visually is something like this. We can flip it 180 degrees, and now instead of canceling out, they effectively double. If this is 1 unit in length and this is 1 unit in length, we're now left with a vector that's 2 units in length. So what that means is that it appears that this flattening occurs when sequential terms have exactly opposite direction, and they therefore add. And we can mathematically describe that as well. So what we're looking for is where these sequential terms approximate 2. These are all unit scaled. So the closer they are to exactly 180 degrees apart, the closer that they will approximate to. So where their magnitude approximates to, excuse me. Now, this specific formula, we can just pursue this same idea. And I'm just being more explicit about what my formula is. If we want the magnitude of a vector, we can take their a squared plus b squared equals c squared, like the most classic formula in all of math. And we want to know where their magnitude, or the length of their vector, approximates to. But this has a nice simplification. So instead of dealing with this, we can instead simplify it to this. So where this approximates to, but you can see that there's still quite a bit of simplification possible. So I'm just going to repetitively simplify this and kind of show you step by step what we can reduce this to. So we can divide out by 2 and square, and we get the cosine of this expression approximates 0. If they're perfectly 180 degrees apart, it will be 0. Otherwise, it approximates 0. Finally, we can continue this as the arc cosine of 0 is pi. Actually, it's pi over 2, excuse me. And pi over 2 times 2 is just pi. So this formula seems to be telling us is that when sequential terms in this sum, or alternating sum, are 180 degrees apart, this flattening occurs and results in an approximation of pi. And the closer that they are to 180 degrees apart, the closer this approximation to pi becomes. Now, for this example, we observe this occurring at 4 and 5. But for 0, 1, we know what this b value is. We know what b value produces the first 0 of the zeta function. So what happens when we plug this in? Just scoot this up. So we have, let me find my notes. (14.134) times the log of 5 over 4, we get 3.1539, which it's not pi, but I mean, that's pretty good. That's 3.15 is pretty close to pi. So our logic seems to sort of be holding up so far. So that's with the first 0. So what happens when we investigate the second zero? Well, we can observe this flattening occurring between 6 and 7, or from 6 to 7. So we can plug in that corresponding b value and the terms that we see the flattening occur. And what is this value? This value is 3.24. So again, roughly approximating pi, but not as good as the first zero. But an important pattern to notice here is that this odd over even integer is exactly the pattern that we highlighted in part 1, aka 2n plus 1, the log of 2n plus 1 over 2n. And we said that it had something to do with the distribution of the non-trivial zeros of the zeta function. So it has reoccurred. So in the next part, we're going to be investigating this formula to see how well it holds up for the other zeros of the zeta function, and to kind of take it to its logical conclusion to see where this formula can get us. I'll see you in part 3. Thanks for watching. So in the last part, we derived and produced this relationship that relates the odd over the even integers and the imaginary part of the zeta function, and where these approximate pi. So the next logical step is to verify that this holds true for additional zeros. And to do so, I made this handy little chart that I'll fill out with you. So, in other words, what I'm asking is that if we put in 14.134, for which value of n do we most closely approximate pi? Now, in the previous part, we determined that that value was where n equals 2, aka 5 over 4, right? So where n equals 2, we have 14.134 times the log of 5 over 4. So it occurs at n equals 2. Now for the second zero, we have that occurring at n equals 3. And at the third zero, or 25, we have 4. And so you can clearly see that this pattern does indeed hold true. And we get this nice little revelation that this formula is not quite right, that we just need to shift it over by 1, aka instead of starting where n equals 1, we start where n equals 2. And to do that, we can just modify our original equation or formula, meaning that the nth zero most closely approximates pi where n equals 1. So in other words, what I'm saying here is that for each zero of the zeta function, the value that most closely approximates pi follows this relationship. Now, the most logical point of investigation is to say, why are we varying n and varying b and seeing where they both line up? We already know what all the integers are. So why don't we just solve this equation for b to see what b should be for each number? In other words, if we take pi divided by each integer input into this, what b would we get? Well, if we take where n equals 1, aka 0, 1, we get 14.078. Womp, womp, womp. It's close, but it is not exact, right? And if we continue this, so instead we solve for b sub 2, or n equals 2, n equals 3, etc., etc. We're in the ballpark, but actually we're getting further and further away. So it seems that by our logic, b of 1 should be 14.078 instead of 14.134. Now, this is why I made this video, obviously, because this is the point at which I decided maybe I needed some feedback on where I'm going with this. However, I do think I know what's going on. So, and to explain, now I can't explain this. How do I want to say this? I think I understand what is happening or what should happen, but I do not know how to mathematically formulate it. So, and to understand exactly what's happening, we have to go back to our original trajectories. So we start on, when we looked at the first 0, we found where this first flattening occurs. And it occurred from 4 to 5. And we stopped. And we said, okay, this is responsible for producing the 0. My suspicion or understanding is that it is not the first flattening, the first time that that sequential turns are 180 degrees apart. It's every time this occurs out to infinity, out to, as you evaluate the sum out to infinity. So presumably another flattening will occur much later on, aka sequential turns will be 180 degrees apart. Same with 0, 2. And same with all the other zeros. The reason, so I shouldn't say the reason, but the first 0 is the best approximation because the first occurrence of the flattening occurs early on. So the sooner the flattening occurs, the greater impact it has. Why? Because the amplitude of this is much greater. As opposed to when we look at 0, 61, the first flattening doesn't occur until roughly term 46, let's say, or term 47. By that point, the amplitude is reduced. So as the zeros, as b increases, the precision of the 0 is more and more spread out, simply because 0, 1 is heavily weighted by the first occurrence of this flattening. AKA, this first occurrence is responsible for 99% or 90% of the alignment. Meanwhile, 61, because the first one doesn't occur until 46, maybe this only represents 50% or 40%. So my objective is to understand how to weight, to first identify each flattening, and then weight them by how soon they occur. Obviously, there's an issue here of evaluating these out to infinity, but it would seem to me that the earlier that the 0 occurs, the more accurate you could get up to a certain term. AKA, you could zero in on the first term relatively quickly. Now, Welcome to the bonus section of this video on the Riemann hypothesis. And at this point, I hope some of you are a little frustrated or aggravated because I spent all this time talking about the zeta function, but I haven't really talked about the Riemann hypothesis itself. In fact, it seems like all I've been trying to do is sort of approximate or predict the zeros of the zeta function. And in doing so, I've just kind of assumed that the real part of S is 1/2, where A equals 1/2. And the statement of the Riemann hypothesis is precisely that all zeros occur when A equals 1/2. But why? Well, this critical line where A equals 1/2 has very specific and particularly useful properties. And I know a couple tricks that I think that might showcase these unique properties. And to do so, the first one, I'm going to return my good old alternating Dirichlet eta function, and I can show you the first unique property by simply taking my leading term and the first two terms in my alternating sequence. So that looks something like this. Now, when A equals 1/2, no matter what B you give this function, you will end up on a point on the circle whose radius is 1, who's centered exactly at the origin. If A is greater than 1/2, let me adjust these a little bit so that there's a better alignment here. When A is greater than 0.5 or 1/2, you get the same circle with the same radius. These are supposed to have the same radius, but I'm not that good at drawing circles. But it's offset to the left. And if A is less than 1/2, again, you get this circle with the same radius, but it's offset to the right. And the degree by which it's offset, either left or right, directly correlates to how far away you are from 1/2. So what? So why does this matter? Well, what that means is that for any B, 1/2 plus any B you feed your zeta function, you will preserve the same magnitude no matter what. You'll end up on different parts of this circle, but the magnitude is always the same because you measure from the origin. However, in all other situations, whether A is greater than 1/2 or less than 1/2, you have varying magnitude. Which means that because you measure from the origin, right? That's how magnitude is defined. So what that means is that for particular values of B, you could get very small magnitudes or very high magnitudes. And if the premise of the zeta function, as we discussed in part 3, is to kind of stack rank all of your terms and weight them upon when they align, then you better make sure that the starting conditions, aka your magnitude, is the same, and that there's a similar decay as you proceed down the terms, which is really only possible where A equals 1/2. Otherwise, you could get a really, really low starting magnitude, which is underweighting anything that occurs at that point. And then finally, I'll leave you with the second little trick, which is sort of my ultimate zeta function party trick. But I say that jokingly because it haunts the inner machinations of my mind. And that is that if you have a system of equations that is x plus y equals 1 and x minus y equals negative x over y. And again, I understand that this is arbitrary. This seems somewhat arbitrary, and that's what makes it a good trick. So the solutions that satisfy this system of equations is where x equals 1 minus 1 over 2 to the s, and where y equals 1 over 2 to the s. Specifically, where s equals 1/2. You guessed it, the critical line. So what is x minus y here? Well, this is 1 minus 1 over 2 to the s minus 1 over 2 to the s, which is equal to 1 minus 2 to the 1 minus s, which just so happens to be the reciprocal of the leading term in our definition of the zeta function. So thanks for watching. I'll leave you to ponder that. Unfortunately, Menaechmus died about 2,400 years ago, so he won't be available to assist. So I'll see you next time. Take care.